All right, so we've built some preliminaries for discussion of um, series solutions to linear equations for second order homogeneous equations and solutions about ordinary points. Let's start looking at some examples. Solve Airy's equation. Okay, one form of Airy's equation is this. Okay. Notice that this is in standard form and it has no singular points. So we could choose to any ordinary point to obtain our solution about that ordinary point. And by the theorem we've discussed in the preliminaries, we're guaranteed two linearly independent solutions about an ordinary point. And so here we're going to choose x equals 0, the ordinary point x equals 0. And we'll do that for pretty much all of them. Okay. So here, let's do this at the beginning slowly, and then we're going to start moving faster. So step one, assume the form of the solution. We assume this form because we're choosing the ordinate. So this is a x minus 0 there, if you will. So we're going to start with this. We're going to compute the derivatives as part of our step one. And since this is second order, we're going to compute the second derivative, and we get this. Notice the shift in the summation index. Plug what we found in the step one into the left-hand side of this. So we're going to focus on the left-hand side. And then we have y prime minus xy is equal to y double prime is minus xy is equal to, well, y double prime is here. Okay. Minus x times y. Now distribute that x. If you distribute the x, you're going to get that n plus 1 instead. Okay, and pay attention to where the sums are occurring. Now, we're going to want to combine same powers. Okay, and we've discussed this in the preliminaries about how to combine power series. So this one here starts at x to the power 0. This one here starts at x to the 1. So we're going to take out the first term of this, and we're left here with that. Okay. And now we want these to start from the same place, as well as have the same index. Okay, so we're going to have, instead of n minus 2, k for this one, so we're going to say k is equal to n minus 2. And solving for n, we get n then is equal to k plus 2, and so we can make that substitution. So ccn here, we got ck plus 2, n, k plus 2, n minus 1, k plus 1. And instead of n minus 2k, where do we start? Well, take that 3, put it in here. 3 minus 2 is 1. Okay? And now we're going to do something similar here. We want to change this to k. Okay? And so this would require us to have k is equal to n plus 1. Solving for n, we get n is equal to k minus 1. And so you see here, there's the k minus 1. And where do we start? Well, this starts at n equals 0. So 0 plus 1 is 1. That's where we're getting that. And now these sums start at the same place, and you have terms proportional to the same power. And so what you could do is then factor out that sum, basically, and you get this. Okay? Now step 4 is to substitute the left-hand side of step 3 into the differential equation and set equal to right-hand side to obtain a recurrence relation. Okay? So this is where the differential equation goes. So far, all we've been doing here is just working on the left-hand side. Of course, the differential equation has a left-hand side and right-hand side. So now this is where we express that whole differential equation in terms of our power series. And I make a note that if the differential equation is non-homogeneous, we would sub a power series of the right-hand side also for a particular solution. But that's just a remark, and I'll say more about that later. So here we have that this differential equation then implies this is the left-hand side that we worked on is equal to 0. And now what do we know? Well, by the identity property, okay? So I could emphasize that, by identity property, we get that the coefficients of these xk's is 0. Not the c sub k's. Okay, the c sub k's, you should not assume that those are 0. But the coefficient of this power term is 0. And there's an x to the power 0 over here too. And so this is 0. Okay? This is x to the power 0 term. And so this has to be 0 by the identity property, and all these coefficients have to be 0 by the identity property. And so solving these, we get c2 is equal to 0, and this solve for ck plus 2 in this equation, and you get ck plus 2 is equal to that, where for what k, and that's an important thing, well, k equals 1 where you're starting. Okay? And this thing here is called the recurrence relation. It just gives you the higher terms, okay, higher index terms in terms of the lower index terms. Okay, future terms in terms of previous terms. And this is just a recurrence relation, and we want our ck's in terms of some base constants. Okay? So we just start with assuming C naught. Okay, let's just suppose we have that, just this base constant. And this is a second order differential equation. So we're also going to not just have C naught, but a C1. And you'll see we need both. We won't be able to express C1 in terms of C naught. Okay, you're going to get two linearly independent solutions. The theorem guarantees it. And so let's start with k equals 1. This gives us the C3 because 1 plus 2 is 3. And 1 minus 1 is 0. And so you just plug in k equals 1 into this formula and you get that. K equals 2 gives us the C4. And that's, so 2 minus 1 is 1, and that's where that's coming from. And so you just plug them in, you get that C1. What about k equals 3? That gives you C5. That's equal to C2 over this, okay? Now, C2 is found, okay? We have C2 not from this recurrence relation, but it was given. It was not given, but we found it from the identity property, okay? So C2 is 0, and so that's 0. And now all subsequent terms are going to depend on C1, C2, C0, C1, and C2, as we'll see. So C6, k equals 4, in the recurrence relation. Okay, don't confuse C sub k with k equals 4 here. So this is of the recurrence relation. This is the index of the recurrence relation, not the index of the CKs. Okay, that's why 4 is not 6. So that's going to give you C6 in terms of C3. C3 we already have in terms of C0, and so it ultimately depends on C0. K5, C7 ultimately depends on C1. C8 depends on C5. C5 depended on C2, and so you'll get that 0, and on and on. And again, how many terms do we have to do this for? The answer is enough, okay? Enough terms. Enough to either recognize a pattern if you want to express the sum in a closed form, okay? Or enough to know that there is no pattern that you could express in closed form, or enough for the approximation you're working with. Like say you just want the first 2 or 3 terms of y, then that's how many terms you'll solve for. So now we have our relations. Now we're going to plug. And notice what we're doing here is going from this recurrence relation to a more absolute relation, if you will, where we have the coefficients now in terms of the base constants that we're working with. C0 and C1 are the base constants, and C2 you could argue, which is just 0. So all other constants will depend on those. So here we then have this expansion, and we're going to now plug in our results. C naught is just C naught, C1 is just C1. Now C2 is 0. We found that from the identity property. What about C3? C3 turned out to be C naught over 2 times 3. And likewise, we could keep going through this. Okay, here I take it really far. Go to the 10th to the 11th term. Okay. And now what am I going to do? Well, what's here, everything depends on either C1 or C naught, which is what we would expect from a solution that has two linearly independent, that's composed of the two linearly independent functions. So I factor out a C naught, so from the terms that depend on C naught, and I factor out a C1 from the terms that depend on a C1. And now I have these two, okay? I'm going to call this Y1, okay? And notice here we have to like take out 1 to be able to express the rest in terms of a formula. And I'm going to call this Y2. Y1 and Y2 are the two linearly independent functions, okay? That form this fundamental set of the homogeneous equation. And again, pay attention to something here. Previously, we found these y1 and y2, and then for the general solution, all we did is just say, okay, well, let's take a constant, multiply it. We'll have c1 times y1 plus c2 times y2. Here, these constants are coming out of just from our procedure to get the solution, okay? They're falling out more naturally, if you will. And so they come as part of the package. And you actually get y1 and y2 by combining the terms that depend on C naught and that depend on C1 independently. And the final step is that if we have an initial value problem or boundary value problem, we would apply the initial conditions or boundary conditions on this solution. We just literally plug them in to fix C naught and C1.